The lecture today is about summability methods. I arrived to summability methods, I don't know how. I solved some questions, but I'm not a specialist on summability methods, right? This is the first thing that I have to talk. And let me to say something about the structure of the talk, okay? First, we will talk about two basic references on summability methods. And next, we focus our attention on two summability methods that historically was discovered in connection with Fourier analysis, right? Namely, the statistical convergence and strong Cesarov convergence. Later, we will talk about our result, which in fact is a principle, is Connor's principle, that we aim this result. And it is based, the talk on this principle in another context, right? Next, we will talk about the question that we solved it, posed by several authors. And we will present the main results, avoiding technicalities when it is possible, okay? Just to present the results. And the main result it is based on two contributions. The first contribution is a revision of the concept of a strong Cesarov convergence modulated by a function. And the second contribution is the introduction of some function which we call compatible modulus functions. Okay, and finally, if we have some time, we will speak about further research about this topic, right? So let us the basic reference. I have to say that this reference I starting to read after solving the problem, and this is the book of Pejerinhoff. And it is included, for instance, some application of summability methods, for instance, for a proof of prime number theorem. Prime number theorem, there are several proofs, and one of them use summability methods. We recommend this lecture. And the second one is a more recent and more detailed book about summability by Johann Buss, okay? In the 90s, published in the 90s. Okay, so we begin with some basic definition. We say that a sequence Xn in a normed space, capital X, is said to be a strong Cesarov convergent to L if the Cesarov means of the differences to the power n goes to 0, right? This concept was introduced in connection with Fourier series at the beginning of the 20th century by Fekete and independently by Hardy and Littlewood, right? This is and the other one is the statistical convergence, was introduced by Estenhaus and Fass in 1951, but some ideas of statistical convergence was already written by Anthony Sigmund in his book of Fourier series, right? And we say that a sequence, it is statistically convergent to a limit L if the majority of the sequence converges to L. And the majority means that all sequence for except a subset which has density 0, right? Specifically, we consider this set, we consider the number k of the sequences outside of a ball, okay? And if this set has density 0, then we say that the sequence is statistically convergent. Let us recall that the density of a subset of natural numbers is the limit, when this limit exists, of the probability of to find an element of the subset A in the interval 1n. So the limit of such probabilities when this limit exists, right? And what is very interesting for me is this result, because Connor's result was discovered a lot of time later in the 80s, and say that both concepts are basically the same. Both concepts that was introduced in different times, in different moments, and by different authors, and by different motivation, are basically the same concept. This is the Connor's principle. Okay, specifically, what he said. If we denote by Wx the set of all strong Cesarov convergence sequences, and S8 of capital X the set of all statistically convergent sequences, then we have this inclusion. Okay? And also, if the sequence is bounded and it is statistically convergent, also is a strong Cesarov convergent. And this subset here can be taken bigger. In fact, can be was sharpened by several authors to be the sharp one. So the biggest has sharp. Okay, the sharpest, biggest of this subset. So even it is this inclusion is for non-bounded sequences. Okay, this is Connor's result. And the idea coming from how to relax convergent methods. This is now the point. How we can relax convergent methods. So we can be less restrictive, and this is very simple. For instance, we can say that a sequence converges to an element if the Cesarov mean of the Cesarov mean, for instance, of the Cesarov mean converges to zero, of the difference, you know? It is very easy to relax convergent methods, right? And what we discovered after our research is that how to be less restrictive. Okay, how we can find summability method between the usual convergence and the statistical convergence. And we can obtain a lot of several summability methods by using modulus functions. We discovered it, but not every modulus function, you know? This is what we discovered, right? And we will, in this position, which modulus function are good to fill the gap between usual convergence and statistical convergence. This is a gap, and we fill this gap with modulus functions, right? Okay, a modulus function is just a function between increasing, okay, between 0 infinite to 0 infinite, which is continuous, is 0 on 0, and satisfy this sublinear inequality. There are several modulus functions. For instance, we can consider monomials, or sum of monomial. Okay, some monomial plus logarithm. We can consider, for instance, log only. We can consider W Lambert functions, which is the inverse of x to the power x, the inverse. We can consider another inverse, for instance, of this function. The inverse is a like of W Lambert function, but more, we can take x to the power s to the power x, the inverse of this function. Okay. And what we will discover is that while this function here does not give you new summability methods, this one gives you new summability methods, and it is possible to get near as we can to the usual convergence by this way, okay? By taking inverse of function that increase too much, right? This is the idea.
Just curiosity. For the first function, the inverse is Lambert function. The Lambert function.
Lambert.
Yeah, for the second.
The second one is a Lambert function type, the inverse of this function, you know? Okay? The inverse of this function. So now this idea of modulus function was formally introduced in the 50s by Nakano. And he said that take a modulus function f, that a sequence is a strong Cesaro convergent with respect to the modulus function if this Cesaro means converges to 0. He put f here in the summation, right? And the history, again, repeats, because 60 years later, Aispuro and co-workers introduced a new density of the set of natural numbers by means of a modulus functions. This formula gives you a density, okay? A density. And we say that if a sequence is statistically convergent to a point modulated by the function f, if the majority again of the sequence converges to L. But majority now means for sets of a subset of f density equal to 0, right? And the question here is the following. Sorry. We have several space of convergence, and the idea is which is the relationship between a strong Cesaro convergence and the new summability method, a strong Cesaro convergence induced by a modulus function, and also what is the relationship between F statistical convergence and the classical statistical convergence, and finally the idea if it is possible to obtain Connor's principle in the modulated history, in the modulated case, right? This question was the first attack of these questions was tried directly, very quickly by several authors, Mikhail Et, Sengul, Barhwat, Dawan, and many others tried to see Connor's principle in the modulated case, right? But they don't obtain it. They obtain it only partial result. And it was a general question to see what's happening, if it is possible to establish or not Connor's principle in such situation, right? And this is the modulated history of the Connor's principle. And the first contribution was the following. We see again that two concepts was introduced by different authors, no connection between them, and it is necessary to get some equivalence to make a slight modification of the original definition of strong Cesaro convergence by Nakano. Okay, this is the first contribution of our work, and we revisited the definition, and this is the concept of a strong Cesaro convergence that fits as a glove to the Connor principle, right? We say that a sequence converges strong Cesaro modulated if this limit is 0, right? This is the first contribution.
Price function.
Yes, f is increasing, right?
So the difference is that instead of n, you put here
Yeah,
F of
yes, but it's not it is because in the definition of the other authors, he put in the definition of the density Fn divided in the question, because they want to be a density, and the density, then the measure of the full set of natural numbers must be 1. So they have to divide it by the f of n. And I keep in account that it is necessary to get the equivalence to divide it by f of n. This is the first contribution, right? If we want to show this equivalence Connor's principle, it is necessary to divide it by f of n. And the second difference is you don't use the triangular inequality in the numerator, right? Okay, and the second contribution is the following definition. For every epsilon positive, we consider this quotient and we consider this lim sup, right? And we say that the modulus function is said to be compatible if this limit is 0, right? This is our second contribution. And our result pivots around compatibility. I say this is examples of modulus functions. These modulus functions over here are not compatible, okay? But this one, are compatible, but this one are not compatible, right? And the interested one are non-compatible modulus functions, as we can see. This is one of the first results. They say that easily we can show that the set of all strong Cesaro convergence sequences modulated by a function is contained in the set of all statistical convergence modulated by a function. Okay, and the problem here was to see the converse, of the result. And we solve the first question to show that both sequences space are equal if and only if the function f is compatible, right? This is the first. If we have only a non-compatible modulus function, we have only this inequality, right? This contention strictly. And equality only when the function is compatible. What it means, but it means that if the function is compatible, no new summability method is introduced, right? We introduce new summability method when the function is not compatible. Second result, solve question 2 and say that these sequences space are equal if and only if again the function is compatible. The modulus function is compatible. And if it is not compatible, we have a strict contention, which is the interesting case, right? And finally, Connor's principle. Connor's principle, the modulated story of Connor's principle is that we have Connor's principle if and only if the modulus function is compatible. If not, we don't have it, right? Okay, in some case, if you have a modulus function for which Connor's principle is true, then this modulus function must be compatible. Okay, this is the characterization. So now we will talk about further research. We have a little time. Oh. Okay, for 5 minutes something, no?
Yeah, you have about
So 10 minutes. Okay. So for further research, we introduce. Well, I don't know. Was introduced by Agnew. The first Cesaro means, which is interesting because to construct this sequence, you only take some part of the sequence. Okay, some part of the sequence. And the only requirement of the interval is that this limit go to infinite and Pn is less than Qn, that it is an interval. So he considered this Cesaro, the first Cesaro means, right? And the idea that some professor from Turkey asked me if it is possible to establish the last result in this contest, right? And this is the new things that we have solved. We introduced this sequences space. With these sequences space are deferred. D is because we take here deferred means, right? And the idea is how this structure before continue being true for deferred means, right? And here we need a sort of compatibility because compatibility is not enough to get the characterization. That's the problem. There are several papers before that used only compatibility that we introduce, but it's not enough to get the full characterization. To get the full characterization, it is necessary to see the following sort of compatibility, right? Again, we consider this lim sup, and we say that the function is PQ compatible if the limit when epsilon go to 0 of this function go to 0, right? And when this sort of compatibility in hand, it is possible to solve many questions, but also it is necessary to introduce this kind of compatibility, what we will call reverse compatibility, in order to obtain different contention of sequences space, right? Which is more or less the same. The only thing is that it is the inverse, right? More or less, right? And with these two sort of compatibility definition in hand, it is possible to obtain more results. For instance, these both sequences space are equal if and only if the function if is PQ compatible, and also we have Connor's principle if and only if the function f, the modulus functions, is PQ compatible, right? So here, some papers. This is the last one, which is submitted, and this is everything. Thank you very much for your attention.